Yeah. Yeah, hello everyone. Welcome to today's ASP seminar. Today we are very happy to have convenient to talk about pLSTM parallelizable linear source translation market networks. Korbinian is a final year PhD student with Cyber written at John Pöppel University at Leeds, Australia. He is interested in making deep networks more capable of and more efficient regarding data and compute through new architectures implemented in CUDA or Triton and more. Let's welcome Korbinian to have today's talk.
Thank you for the kind introduction to you. I'm happy to present here at the ASAP seminar my latest work on parallelizable linear source transition mark networks, so pLSTM. It's related to the original LSTM, no worries. We'll see why. So as an intro, I want to give you a quick reminder on linear RNNs. I think they have become quite popular in the past years with QLSTM, DeltaNet, LRU, RWKV, GLA, Mamba, Griffin, MLSTM, Gated DeltaNet, TTT, Delta Product, and probably quite many more. And at their core, we have this memory cell here at a node of a network and depicted in pink. And we have an input for this current sequence point that is scaled with an input gate. We have the previous state from a previous node that is scaled with the forget gate. And we have an output gate that scales or translates this cell state to a hidden state or an output of the network. And because there is no hidden state dependence of these gates of the input, forget, and output gate, and also like the input into the cell, this can be parallelized by unrolling the sum of all the past states, and this is can also be done in a chunkwise parallel fashion that is hardware optimal, and there has been quite some research on how to make that efficient. And actually, Songlin Yang, who's hosting the session, did great work on implementing many of these networks efficiently with Triton. So these linear RNNs, they are recurrent neural networks working on a sequence inherently. But we have seen them being applied also on non-sequence data. Like, for example, here in computer vision with Vision Mamba, Vision RWKV, Vision LSTM, images are not really a sequence. They have 2 dimensions, and there is a neighborhood relationship in these 2 directions that they have. Or actually, if you think about isotropic architectures, it's even going beyond just having these 2 directions. So how are they applied there? And actually how this works is that you have here, if you look at the right parts, you have basically this grid of patches, and you go over them in varying sequences from like line-wise or column-wise, or with the skip in the last one. But and that's what I want to visualize here. None of these really captures this directional relationship that you might have in images. For example, in the arrow pointing task. That's actually a task that we propose in this work. It's a very simple synthetic task that tries to capture how well models can generalize in multiple dimensions for extended sizes in a directional fashion. So you have here on the left an example of this task. It's very simple. You have an arrow and you have a circle, and you're trying to classify if the arrow is pointing towards the circle. And actually, in this case, it's pointing slightly away from the circle. So this should be classified as non-directing. And all of the methods that go over this in a sequence, they might lose this directional information when jumping over lines, jumping over columns, or whenever this is sequentialized in a path, there might be close by relationships. Actually, for these cases, diagonal relationships that are not captured well. So yeah, can we resolve this? Can we maybe even extend linear RNNs to multiple dimensions as we have it for images? And actually, it is the case. It has been done quite a long time ago with multidimensional RNNs and multidimensional LSTMs, with work from Alex Graves in 2007. This was actually probably among the first deep learning successes even in computer vision. And yeah, there Alex Graves applied this two-dimensional LSTM on Arabic handwriting recognition tasks, and actually won a challenge there, or won a competition there with this deep learning architecture back in 2007. So yeah, one key point here is also that this is actually still a nonlinear RNN. So you have to go over this patch by patch, or there's actually this wavefront algorithm where you can parallelize a bit, but it's maybe not as well suited for modern hardware. That's why we look into we will look into if we can make this more efficient with a linear version. What's also interesting is that this has been extended even to non-regular multidimensional structures, like general directed acyclic graphs. And yeah, there it has been used for, I think, semantic relationships in text, actually. So yeah, can we combine the ideas from linear RNNs that have emerged in the past years with these multidimensional RNNs? And we want to have a parallelization. So we want to be hardware efficient. That doesn't necessarily mean that we have few flops, but that means that we parallelize a lot to leverage GPUs. Then also, can we do this with long-range stability? And we will see later why this might be a problem. And also with a directional propagation. So what you could always do, as you do with a transformer, you just create a fully connected graph of your inputs, and you connect everything to everything. And then you have you have long range stability, let's say, but you don't have this notion of direction that you have naturally in these graphs or also images. And yeah, we can do that. We can combine all of these three. So what do we do to make this happen? First, we modify the gating structure of linear RNNs. So on the left, you still have this sequence where you have inputs, and they're also depicted, or they're also nodes in some sense, and also depicted. with these pink circles. And you have the, as previously mentioned, input, forget, and output gates. I didn't mention it before, but this very easily translates to structures in Mamba, for example, with the ABCD gates. Yes, so this, yeah, can be all captured here. We now do this gating on kind of on the line graph. So the line graph of a graph means the graph that is constructed of the edges of a graph. So if two edges are adjacent to the same node in a graph, they're adjacent in the line graph. And how these gates operate is that for every node we have an input, and this is connected to outgoing edges with a source gate. Then between pairs of edges we have the transition gate, and then from an incoming edge at the node to the output at this node we have the mark gate. So yeah, how does this look like on a sequence? For linear RNN, you have these inputs basically at the nodes. Then you have these forget gates. Then you have this output. For pLSTM on a sequence, looks a bit different, but it can, it can probably be well translated into one in each other with reparameterization. So, but how does this now look like on a graph? There we now have these structures, these sources, these transitions, and these marks. And here it's visualized again. The source connects a node with outgoing edges. The transition connects incoming edges with outgoing edges, and the mark connects incoming edges with the output. How do we compute this? Because we have a directed acyclic graph, there is a topological order of this graph. So we have guaranteed that there is basically an enumeration of the nodes. So what we can do is we go over this enumeration of nodes, and at the current node, add source contributions to outgoing edge states, add transitions from incoming to outgoing edge states, and then compute the mark from the incoming edge states for the network to the output of at the current node. And then we iterate over the sequence of the nodes in the topological order, and we can compute the output. So that's quite simple, but that's recurrent. So it doesn't leverage the parallelization power of modern GPUs. So a naive parallelization would be, well, we know all of this is a linear network. So essentially this means that an output at a node is a weighted sum with source transition and mark gating of all parenting nodes, all parenting node inputs. And so what we can do is we just sum all these paths from all incoming nodes to all outgoing nodes. And that's it. We can parallelize this. The problem here is that there are exponentially many paths for a multidimensional case. So if you imagine an image, in an image, at every patch or pixel, you have, in like assuming that we go causally from left to right and top to bottom, you have two outgoing neighbors, and then you also have two incoming neighbors at the top and at the left. And so going one step further diagonally leads to a multiplication of the paths by a factor of 2. And this is why it's growing exponentially. So essentially, it's these diamond shapes that you have in arbitrary darks that multiply the number of paths. So what you can do now, and I want to introduce here the notion of the loosely self-similar dark. So what we want to do essentially is we want to use basically a divide and conquer approach to tackle this problem of these many paths, and partition our original graph into subgraphs and then for each of these subgraphs we can do our computation in parallel, and then later on only connect them via their connecting edges. So here, for example, you have here these 3 subgraphs in the light gray, brownish gray, and darker gray visualization. And for each of these, we can actually compute first the internal path, and then we connect this via the interconnecting edges. And if we can decompose our graph self-similarly such that edges don't scale, the number of interconnecting edges doesn't scale larger than the number of nodes that we cover in the subgraph, then we are on the safe side that actually this parallelization makes computationally sense. Otherwise, it will just lead to more computation overhead than what we gain. So here I want to visualize this again. Lots of these puzzles basically. So what we can do with actually the source, transition, and mark gating system, we can create this higher level source that now connects 2 incoming edges with the 2 nodes with these outgoing edges, sorry. And this is via the sum of the single source contributions and this combination of a source and a transition here. So this source transition combination now connects this lower incoming node with these upper outgoing edges. And we sum over this red triangle that connects these 2 nodes, and summing all of this, we then have this higher level source. And we can do the same thing also for transitions. Here we just combine single transitions and combinations of transitions that connect these interconnecting incoming edges and interconnecting outgoing edges. And for the mark, we have the similar structure again. Now it's just that we have first a transition that then goes into a final mark. And if we combine all of these, we get this high level structure of this mark object of a higher level. Ultimately, what we arrive at when we then in the end combine even these source and mark terms is actually the gating matrix. And this is, if you are familiar with more familiar with the attention formalism, this acts like an attention mask if you think of alibi encodings, they also act basically as a mask for the attention, an additional factor on the attention matrix. And this is here very similar. And this gating matrix is basically just the combination of source and mark terms at all levels, and tells us how source nodes are connected to target or outgoing nodes, or inputs at certain nodes are connected to outputs at other nodes. How this looks like on regular grids, for example, images, is that we here also use a directed acyclic graph. So we go here from top left to bottom right, and then actually combine also this with the three other versions. So top right to bottom left, bottom left to top right, and bottom right to top left. And how the sources, transitions, and marks look like is shown here. So we can have this these terms here in a matrix vector notation formulation. And there is basically a source that lives on these green edges that are in between pixels, that and the source actually is a connection from a node from this pixel to such an edge. The transition is shown here with these arrows, and there actually is 4 transition terms in general for this for this grid. And then the mark terms are basically from the edges to these outputs at the nodes. How the parallelization looks like in 2D is that also here we can, if you look at top down, we can decompose our image into smaller patches. Or if you look bottom up, as we do maybe here, is that we can combine multiple patches, the inputs of multiple patches here, this larger source term covering 4 input patches. We can calculate this source term via the combination of all these path combinations that are shown here on the right. And we can do the same thing for the transitions, and we can also do the same here for the mark terms. And what is crucial here is that each of these source terms here on the right, for example, on the right top, is actually more than one path. So here on the left, we even have 2 paths. So this source combined with 2 transitions in 2 directions, and so on. Here, the vanilla source terms without transitions. Here, the combination of one source with 2 transitions, and here again, the top right and bottom left patch going to the bottom right outgoing edges. And what is important here is that we can do all of this just with einsam operations and concatenations in Torch or in JAX. And actually in JAX, we can leverage the very powerful XLA compiler to then make this run quite fast. Now we come to the second important part of our work shown here, that is long-range stability. For a sequence, it's very simple. We just have this sequence. We just have one direction. And if all transitions along the sequence are bounded by 1 or by something that has kind of a norm 1, we know that everything stays sound, stays bounded. For this multidimensional case, however, we cannot just look at the single transition levels, because we actually have potentially many paths. Actually, for this 2D case, it's already exponential. There are these two options, as I explained before, and we have this exponential activation blow-up. So what can we do? And there are actually, as we find, there are two fundamental options to stabilize this. And the first one is the P mode. It is the L1 norm on transitions. How can I motivate this? The P mode basically takes the edge activations at the node and then limits how they're distributed outwards of this node. And if we look at how this propagation works on a graph level, is actually that the transitions form the adjacency matrix of the line graph, and the operation of pLSTM then is that we sum up, we have a power iteration of these adjacency matrices in powers. So we have some sources at all the edges, and then we subsequently apply more and more transitions on them and add all of this up. And now when we limit the L1 norm of this transition adjacency matrix, we know that his matrix multiplication of the L1 is submultiplicative with respect to the L1 norm, the rho norm, and this way everything stays limited. How does this look like for images? Actually, for images, this also has a very nice geometrical interpretation, because what we do here is that we sum up these terms for every node. We sum up these terms of these transition terms, and they must be 1 for the propagation to be stable, or smaller than 1 for an exponentially decaying, but at least not exponentially exploding propagation. Now, if we even go one step further and limit the structure to this form here, shown on the left, bottom left, we arrive at a propagation, a directional propagation along a line in the image. So imagine we have these transitions fixed, and for every position we have this form with a fixed alpha. This then means that the receptive field, the effective receptive field of this top left pixel here, shown in bright yellow, goes along a line with an angle defined by alpha, by this entry of the transition matrix. And with this, we have directional propagation. So we can encode the direction, the notion of direction here in the propagation along a line. And actually, this moving along a line would similarly work also in directed acyclic graphs. Similar idea was already explored in Mamba 2D, but they fix the angle here at 45 degrees. So actually, it's all 1/2 here. And this is why, this is a bit less expressive as the P mode of pLSTM. Now, I told you this is not the only way of how to stabilize this, because what is the problem here? We can only move along one line. If we have this top left pixel here or patch, and we want to propagate information to all causal children of this input patch, we cannot do that with the P mode because we can't just move along a line. So the second way of how to make actually to enlarge the receptive field while losing the notion of direction is with the D mode. So we fix the transition matrix here to this structure. The gamma terms here have to be 1 for a stable propagation for a long range, but can be smaller than 1 in norm. And by fixing this bottom left entry of the matrix to 0, we remove this connection from the top to the right of the transitions. And this way, all the paths in the graph, or in the line graph actually, are reduced to these L shapes. And there is actually just one path between this incoming node or input node towards an output node. This we can also do on directed acyclic graphs. And there, what we do is that we prune the line graph to a multi-tree. So multi-tree just means that we reduce the edges in a way such that in the end, there is only one path from one edge to another edge. And this way, we know that there is just this one path. There is not this exponential explosion of paths. And therefore, we can just limit the transitions, the single transitions by 1. And therefore have stable propagation, signal propagation in the graph. What is interesting, I think, is that this analysis also goes beyond just pLSTM, but this applies to general computational graphs. Every finite computational graph can be unrolled to a dark. So all machine learning models, for example. And what we have for machine learning, for deep learning especially, is that backpropagation uses gradients. And gradients are linear approximations of the computation in the graph. And because it's all linear, this means that also this analysis of pLSTM applies and shows that probably in quite many typical neural network architectures, we have this vanishing gradients, and we don't have a stable propagation for very long ranges. I think that this is also related to, for example, the positional bias of transformers when they're going very deep towards the first tokens. Now let's come to an application of pLSTM actually. First to this synthetic benchmark, this arrow pointing, and actually arrow pointing extrapolation that we use. So we have these images of arrows and circles, and we train on a certain resolution for until convergence basically, and then we test on 4 times as large images with arrows and circles being still of a similar shape, but the image is just larger. Now, we want to test basically can networks and which networks can do this extrapolation generalization in multiple dimensions on this directional task. And we can show that quite many networks can do very well in interpolation, so training on a certain scale and then also testing at that scale. Actually, EfficientNet, very famous convolutional deep network architecture, is very good here when testing at the same resolution as we trained for. But then when we go to larger images and try to extrapolate, we see that actually this structure of pLSTM having these directional components with the P mode and also the D mode for global distribution outperforms all these competitor models. And interestingly, also 2D Mamba and Mamba 2D cannot really solve this task very well in extrapolation. We also show that our model can be scaled to many inputs of high dimension, like ImageNet as a very important computer vision benchmark, and we can show that pLSTM performs roughly as well as long-tuned transformers or also competitive architectures like Vision LSTM. And there would be still a room for improvement by optimizing the training schedule and also the backbone. So we have here an isotropic backbone or a non-hierarchical backbone. But in computer vision, it's actually quite common to have a hierarchical backbone because it leads to better results. And we can also show, because pLSTM works on general directed acyclic graphs, we applied here on standard graph benchmarks and show that it has comparable performance to established models, and because of its parallelization and its long-range capabilities, might be interesting for the future, for actually maybe graphs where especially long-range interactions are important. So with this, I want to conclude. The contributions of this work are: we translate linear RNNs to multiple dimensions and general direct acyclic graphs, including a parallelization scheme that resembles what we have with the parallel associative scan for sequences. we derive long-range stabilization modes for these linear networks on darks. So in particular, the propagation or P mode that has a direction, and the D mode that is called distribution mode because it has a full receptive field still. And we propose this arrow pointing extrapolation task as a synthetic benchmark for long-range directional capabilities. Especially focused on generalization for extrapolation. Limitations of our work is that we could further investigate the solution modes of pLSTM and others on this arrow pointing extrapolation. I think it would be quite interesting because it's such a simple task to look at how actually networks can solve it or fail to solve it. There are, of course, improvements to be made on benchmarks, and potentially there are even harder real-world benchmarks that need this long-range multidimensional relationships that we could look at. And yeah, this would be the bibliography, and now I'm happy to take questions. Thanks for your attention.
Thank you very much. That if you have let me design that. Yeah. Now I think all people can unmute themselves or send the questions in the chat. Yeah, and to ask questions. Yeah, I think there are 2 questions in the chat. Have you answered? Yeah.
Yeah. Thanks. Is the gating matrix an adjacency matrix, or is it more sophisticated? Essentially, if you can also look at pLSTM from the perspective of message passing neural networks. But with pLSTM, we don't just propagate to the nearest neighbor, but we propagate to all nodes that are downwards in the ancestry. So we do basically a full range propagation in one layer. And this way, we somehow construct an adjacency matrix that captures all powers of the original adjacency matrix in a graph, let's say. This we can only do because we restrict ourselves to a directed acyclic graph structure, because otherwise with loops, you would have infinite loops at some point. But with a directed acyclic graph, you know that the powers of your adjacency matrix at some point go to 0. That means basically when you start from one end of the graph, at some point you have reached the other end of the graph because there are no loops. Yes, that's so far regarding the first question. I hope I could answer that well. And for slide 21, 22, or actually it's also here. So the subscript X and Y here means if we are on X would mean the X edge here for the source, and Y would mean the Y edge, so the bottom edge. For a mark, it would be kind of similar. It would be, let's say, for this term here, the mark would be the incoming edge, so the X edge would be the left one, and the Y edge would be the top one. And for the transition, XX means going from left to right, and YY would mean going from top to bottom. And you also have these off-diagonal terms with xy going from left to bottom and yx going from top to right. Yeah.
Yeah. I think maybe
Oh,
I have
yeah.
I think maybe I have a question because I'm from your design I meant you see that you said the cell state on the edge, yeah, and it says the output on the node, yeah.
Yes.
And but if you want to have this design, as you mentioned, the problem is that because if, for example, if you have n nodes like n tokens, that the complexity of the adjacent matrix can be at most n squares. So we need to make this graph sparse to avoid too much edges. But I'm thinking about that, so that I think this somehow maybe restrict maybe the flexibility of the deck structures. I was wondering why you choose to set the cell state on the edge instead of the node. I think that you can also maybe upgrade, you can have a initial state of each node and upgrade to maybe all past the states that by using the edge that would you have an information flow to aggregate this information that to update one node. Yeah. I think maybe this is also another possible way. Yeah.
So you mean basically that we have cell states here at the nodes
Yeah, yeah, that's right.
and then propagate from node to node, right?
Yeah,
Um, I think ultimately, if you would then aggregate this to like more cell states of this higher level structure, what ultimately, like if you would decompose your graph
I see.
like
Yeah,
here, ultimately you would at some point, even though you compute your or you move your cell states to the nodes, if you do this decomposition, you would still have like these connecting edges. And
yeah,
then what you would effectively do, I mean, it's a bit too small of a graph here, but you would then take all the states at these boundary nodes, so nodes that have a boundary edge, and then
uh,
propagate the state from this boundary node to this boundary edge, right?
yeah, yeah. I,
And yeah, so in the end, it would kind of look like the same, but you would have basically here. I think what would also be a limitation of this approach is that you would then have because let's say these two edges would then have um, the same cell state, right?
I see.
Because it comes from this node.
Yeah, yeah.
So it might be harder to encode the notion of directionality here
I see.
because they share many edges would then share a similar state. But I think it could be done. I think there's no principal way to rule this out, but I think it wouldn't work as well and would be harder to derive a scheme even
I see.
to
Yeah, I
parallelize
think
it.
that both is acceptable, can be parallelizable. Just I guess maybe just I think that maybe it's like to maybe increase that increase maybe the complexity of the whole information flow from node to edge then to the node. I guess that maybe it will be more powerful. Yeah, I'm not sure about this. Yeah, I think maybe the reason. Yeah, because that if you think about a node-only transaction, that it is first that if you start with a softmax attention, a standard one, that because that each token will have we calculate them cosine similarity, so that they will form a adjacent matrix. If we set some positions to be sparse, then the sparse match attention map will representing some maybe deck structures. Yeah, if with causal restrictions. And then if we further replace the softmax, then I think that we have maybe a very trivial node connections that without any decay. Yeah. So this is the reason why I'm thinking about this. Yeah.
It's yeah, very very interesting connection, because yes, ultimately yes, you could also look at the attention matrix basically as an adjacency matrix of a fully connected graph, and then
Yeah, we can prune and then we remove softmax. We have a DAG, maybe a DAG linear RN, yeah, it's a simple one. Yeah.
yeah
Yeah, I think
probably
yeah.
sorry.
Yeah, yeah. No, I just mean that, yeah, I think this makes sense. And I think that there's one more question in the chat that mentions that in the 2D P mode, the network length propagation angle alpha. How does the model's performance depend on the initialization of this angle? Can you give an intuitive interpretation of that angle?
Yeah, that's a very good question. Unfortunately, I have not run ablations on this, so I cannot tell you. How it is currently initialized is that we have, as for transformers and linear RNNs, we have multiple heads, and also this state expansion, aka key query associative memory. So yeah, but we have this, we have these heads, and how it's initialized is that there is a bias for each head, such that there is a line for each direction. But unfortunately, I have not run an ablation on if this actually improves the performance or not. But I think it's quite essential, especially for the P mode, because it has this restricted receptive field, that you initialize it in a way such that information can propagate in the beginning, so that the model can learn something. Because if you have a very strong decay, we all know that also from linear RNNs, that if the forget gate or the transitions are initialized in a way that there's a strong decay, then the model will have a very hard time learning anything. Yes. And the intuitive interpretation of that angle is, basically that it gives this direction, and it actually can change the direction along the path, given the current inputs, because the angle is not fixed; it's input dependent, as all of these gates of nonlinear RNNs are input dependent typically. Yeah. Any more questions?
Yeah, very good job. Question.
Hi, it's me. I have a question. First, in the slides you did you introduced a little bit about the 2D P mode. Would there be like a 3D P mode or maybe 4D?
Sorry. Yeah, of course there could be. I think what is crucial for the P mode in 3D or in 4D would be that information would still just be able to kind of move along one line, for the P mode as it is. So if you have imagine you have a 3D cube where you have, I don't know, voxels, then for the P mode, information would still just move along one line. The receptive field would be just one line. For 3D, one could actually even, that's another thing. For 3D, one could even imagine kind of a combination of P mode and D mode, that would then be somehow in between. So in what you could do, I think, is that in 2D slices, you would use a P mode, and along the third direction, you would use a D mode. But yeah, so maybe there might be something in between there. I'm not 100% sure, but it could be, yes. So but both of these modes equally well work in 3D or 4D or even more. But there's this caveat that for the D mode, you have no direction, but a full receptive field, whereas for the P mode, you have this direction, but you can, with the receptive field, just move along a line. Yeah.
I saw some research on like they're trying to like explain the reasoning ability of a transformer-based model, because I think their observation is that transformer can like simulate the finite state automata. I think it's similar to your work. Do you think that maybe there's some similarity between those, and whether your proposed like P mode or D mode, whether they can maybe explain the reasoning ability of the foundation models of the DN models?
I'm not actually quite sure to which work you're referring to, but I think for like if you just look at sequences and you look at transformers, transformers are deep architectures. So there is this extension with the ResNet architecture in depth. And so ultimately your network is also 2D, because you have the sequence dimension along X, so to say, and the depth along Y. And so, as I mentioned, I think for this position bias of transformers, I think this analysis provides a nice explanation, or maybe an additional explanation. I think there have been quite many other works that analyze this more focusedly. But regarding reasoning, are you referring to images, or are you referring really just to sequences?
For reasoning, I mean the reasoning task for NLP, like a chain of thought, where because the reasoning process is kind of like a to transit from the one state of the finite state automata to the state that you want to. So it's kind of like that, but I don't know, like yeah, I see there maybe there's some potential for this to maybe to explain more about the reasoning ability of NLP tasks. But
might be, yes. I think because if you limit the number of computations, ultimately all, as mentioned here, all computations can be enrolled to a directed acyclic graph, and then at least for backpropagation, this pLSTM analysis holds for anything that is nonlinear in a forward. It holds to the limit of a linear approximation. Yes.
Okay.
So, and yes, for finite state automata, there, yeah, I think the most interesting part there is how multiple transitions in finite state automata work, and how maybe transformers can. I think there has been some work, maybe you're referring to that, about transformers recognizing that they have arrived at the same state again as they were before, like going in a loop in this finite state automaton.
Yes.
It's basically about equivalence classes of these states, and but that's also something that pLSTM will not be able to solve as it is here, because it is only a dark, so it cannot loop infinitely.
Okay. Thank you.
Yeah, thanks for your question. One more question.
Yeah.
Yes. P mode constrains subgradients from exploding. Could you explain how it also addresses vanishing gradients? Yes. So I will repeat the question for the audience. So could you explain how the P mode addresses vanishing gradients? I think it doesn't address it right away, but because we know that if all the transitions have norm exactly 1, we actually know that there can be long-range propagation. It's, at least for 2D, this was also shown in the appendix of the paper, that for the P mode, the signal does not decay exponentially when all transitions are set to 1 along that line, but actually just decays as a square root. So there's still kind of vanishing, but at least not exponentially. When you go to higher and higher dimensions, I think this analysis, at least for regular grids, will then be still the same, just with a different exponent. So it will be still a polynomial, a power law decay, but not an exponential decay. And how we leverage or how we avoid vanishing gradients is actually that we set a parameterization that tries to keep these activations very close to 1, and we initialize also in a way such that these transitions have this norm very, very close to 1, and only then during training, it can learn to avoid this. Similar to how the forget gates are initialized for a linear RNN, or did that?
Yeah.
Thanks.
Is there more questions? Yeah, it's check. If it's no more questions, I think that we can end here today. Thank you very much for the great talk. Yeah, I think it's very interesting to extend it from sequence to a deck structures, because I think that deck is actually the thing can represent this word. Yeah.
Yeah, thanks. for for the kind words. And yeah, I hope I could convey the ideas well enough. And
Yeah, for sure.
if you have further questions, feel free to reach out. I mean,